All right, here we go. Unit 5, Lesson 7. We're moving on to a new topic. We're going to be talking about exponent rules. Today should be mostly a review of exponent rules that you know from Algebra 1, hopefully with a lot of additional context to help you really understand them rather than just memorizing the rules. Before we get started, I just want to really emphasize one important thing. When we talk about exponent rules, we're talking about rules that apply when we perform operations, and this is really important, on two numbers or variables with the same base. What I mean by the same base, right, is as a preview of the product rule. The product rule says that if you multiply two terms that have the same base, you can add their exponents. So x squared and x to the seventh, the base of both of those is x. And so since they have the same base, we can add their exponents. Same works for numbers. If we have 5 squared times 5 to the third, it's a base of 5. We can add the exponents when they multiply. This would not apply to x squared times y to the seventh because they are not the same base. Okay? So here we go. We're just going to go one by one. The first one, we just kind of previewed it quickly, is the product rule. It says that if you have two terms of the same base, if you multiply them, you add their coefficients. And so, for example, x to the third times x squared would be x to the fifth. Now, this is not something you should feel like you should have to memorize, right? It should just kind of make sense because what is x to the third? It's 3 x's being multiplied together. We're going to take all of that and we're going to multiply it by x squared, which is just 2 x's being multiplied together. And so if you have 3 x's being multiplied together times 2 x's being multiplied together, count them up, you have 5 x's being multiplied together. That's why the product rule works. And so, like our rules that are going to follow, remember the exponent rules, they only apply to the exponents. So if we have coefficients, they work like normal. If we have 3x to the fourth times 5x to the seventh, that would be 3 times 5 to make 15, x to the 4 plus 7, 11th. Now, once again, you could really break this up to see it. This is 3 times 4 x's times 5 times 7 x's. When you break it up this way, you can really see why the exponent rule only applies to the variable term that has the exponent and not the coefficient, because altogether we'd have 3 times 5 is 15, x to the 11th. If you do this with multiple variables, so this would be like the hardest level problem that we have on Delta Math, negative 16x to the third y squared times negative 4x squared y to the fourth. You just go term by term. So first we have the coefficients. Negative 16 times negative 4 is 64. X to the third times x squared, we would add their exponents to make x to the fifth. And y squared times y to the fourth, we would make y to the sixth. And again, you could multiply it. You could do the whole breaking up thing like I did above. But at this point, you should be convinced that, yes, this is going to work. All right, so that's the product rule because product means multiply. Next would be the quotient rule. Quotient is the result of a division problem. So the quotient of 10 divided by 2 is 5. Okay, so quotient is the result of a division problem. And the rule here is that when you divide terms of the same base, we subtract their exponents. So if you had x to the 6th divided by x squared, it would be x to the 6 minus 2 would be to the 4th. But once again, not something you should feel like you have to memorize, because if you break it up into what's happening, on top we have 6 x's being multiplied together. On the bottom, we have 2 x's being multiplied together. And so, our normal cancellation rules apply. X divided by x is 1, so it goes away. X divided by x is 1, so it goes away. This would be x to the 4th. So our normal rules of cancellation are what give us the quotient rule. Just like with the product rule, if you have coefficients, the coefficients get divided just normally. So 10x to the 7th over 5x squared would be 10 divided by 5 is 2. X to the 7th over x squared would be x to the 5th. Now again, you could take this and you could see it as 10 times 7 x's, 3, 4, 5, 6, 7, all over 5 times x times x. So if you're ever not sure if you remember the rules or not, Now you'd have 2x to the fifth. You can always expand it out like that. Once again, we can have problems. So this would be like the highest level problem we have on the delta math. You can have problems that combine multiple different terms. So 8x to the 8th y to the 7th over 2x to the 6th y to the 6th. 8 divided by 2 would be 4. We have 8x is being multiplied on the top. 6x is being multiplied on the bottom. This would be x squared. We have 7 y's being multiplied on top, 6 on the bottom. 6 of them would cancel, leaving us with 1 y on the top. Right? So you can either think of it as canceling or you can use your exponent rules. Now, what this sort of brings to light is what if we had more of a certain variable on the bottom than on the top? And so we're going to need a separate way of dealing with negative exponents. And so we're going to use this example of x to the third over x to the seventh to show why the negative exponent rule applies. So a negative exponent represents 1 over the same term with the positive exponent. So x to the negative a is just 1 over x to the a. So as a quick example with a number, 5 to the negative second is 1 over 5 squared, or 1 over 25. And the reason that this is how negative exponents end up being represented is, take a look at this one. If we had x to the third over x to the seventh, and we try and apply our breaking up procedure. So we have 3 x's being multiplied on the top, 7 multiplied on the bottom. 5, 6, 7. So x divided by x is 1, x divided by x is 1, x divided by x is 1. A lot of times people will get confused here and they'll say, oh, there's nothing left on top, which is not true, because what you're really doing is dividing the numerator and the denominator by x, which leaves us with 1, right? It's like you had an understood 1 coefficient that's still left up here. So this would be 1 over x to the fourth, right? Well, 1 over x to the fourth is one way of writing that answer. But another way is just to apply our exponent rules. If we did x to the 3 minus 7, like the exponent rules say, that would be x to the negative fourth. So that's why x to the negative fourth and 1 over x to the fourth, those are the exact same thing. Now be careful, some delta math examples will say, write your answer with only positive exponents, and we'll see an example of that in a second, and that's what they mean. Take all of your negative exponents, move them to the other side of the fraction, either the numerator or the denominator, so that you only have positive exponents. So let's see here. Same thing. Be very careful. This negative 4 does not apply to the 3 unless there is a parenthesis. So this right here just means instead of 3x to the negative fourth, it's 3 over x to the fourth if we write it as a positive version. Now, if we had 3x to the negative fourth like that, that would be a different story. That would be 1 over 3x to the fourth, which would be 1 over 3x in parenthesis to the fourth, which would be 1 over 3x times 3x times 3x times 3x, which would be 1 over 81x to the fourth, but we're not dealing with that today. That's going to be something for tomorrow. But for right now, just make sure if there's no parenthesis there, the exponent does not apply to the coefficient. Okay, so just real quick here, here's an example from delta math. If we had 12 over 20 x to the 8th, 12x to the 8th y over 20x y to the fourth, 12 over 20, right? You can either do this in the same one or you can try and break it up here. If we had 12 over 20, well, 12 over 20, 4 goes into both of those. This is 4 times 3 over 4 times 5. So this is 3/5. So we'd have 3 over 5, and we would just fill in. X to the 8th over x, we would have x to the 8 minus 1, we'd have x to the 7th. Y over y to the fourth. Now here's where I'm going to give you 2 separate ways of thinking about this. One way is just to kind of break this up into what's happening. We'd have a y on the top, and we'd have y times y times y times y on the bottom. Well, one pair of y's would cancel, and we would have 3x to the 7th over 5y to the 3rd, right? It's just where are there more y's on the bottom? When they cancel, you'll be left with 5y to the third. Or you can apply your straight exponent rules, right? You just go straight through. You say this is 3/5, x to the 8 minus 1 is 7, y to the 1 minus 4 is -3. And then you can convert that into 3x to the 7th over y to the third by moving this down here. Either way is an acceptable way of thinking about that one. Okay, we have two more rules. One is really quick, and then one is a big one. Another thing that happens here, right, if you follow the logic of the quotient rule, if we had x to the fourth over x to the fourth, we would have x to the 4 minus 4, which would be x to the 0. So we need an idea for what does this x to the 0 mean? Well, we know anything divided by itself is 1. So what that means is anything to the 0 power is 1. Literally doesn't matter. 15x to the third, if it's to the 0 power, 1. Anything to the power of 0 is 1. And so if that happens in the course of, right, a bigger problem like this, 12x to the fourth y to the fifth over 3x squared y to the fifth, we would have 12 divided by 3 is 4, x to the fourth divided by x squared is 4x squared, and y to the fifth divided by y to the fifth is y to the 0. Well, that's just 1, right, which makes sense because these would just cancel in another way of understanding that because they become 1. So the final answer here is 4x squared. Okay, last one for today. Last one is a power to a power. So if you have a term like x to the a and you raise it to the power of b, that's when the exponents multiply. So if you had x squared times x to the third, right? Just following the rule, this is x to the 2 times 3. This is x to the 6th. Here's y. Remember, to the third power means times itself, and times itself, so that there are 3 of them. Well, now we could apply our product rule. X squared times x squared times x squared, we would add their exponents, x to the 6th. So that's really all that's happening here. If you have 5x to the 5th to the 3rd, right? One way to think about this is to not even bother with the exponent rule. This is just 5x to the 5th times 5x to the 5th times 5x to the 5th. We would multiply the 5s to get 125. We would add the x exponents to get x to the 15th. If you're just doing this from the exponent rules way, you just have to remember the power applies normally, right? This applies normally. This means 5 to the third. 5 times 5 times 5 is 125. But then the exponent rule applies when it's x to the 5th times x to the 5th times x to the 5th. That would be x to the 15th. And so the very last example for today, just tying this all together, I'll do it once just showing the exponent rule way, and then once breaking it up. If we had -4x to the fourth y to the fourth, all to the third power, just using exponent rules, this means, so I kind of think somewhere else on my paper, okay, -4 to the third power. Well, that's -4 times -4 times -4. That's 16 times -4. That's -64. So we'd have -64, and then the exponent rules apply. X to the fourth to the third, multiply. X to the 12th. Y to the fourth to the third, multiply. Y to the 12th. And lastly, the reason this happens, if you write this all out, -4x to the fourth, y to the fourth, times -4x to the fourth, y to the fourth, times -4x to the fourth, y to the fourth, right? And obviously, like if this is to the 10th, this becomes impractical. If you just multiply these 3 things, you would get -64 product rule from multiplying all these x's. 4 plus 4 plus 4 is 12. 4 plus 4 plus 4, y to the 12th. So those are your rules. You'll have some Delta Math ones to practice, and that is it for today.